Introduce myself. My name is Michael Reinhold, and I am the session moderator for the SSA Tech and Decision Making session. Again, we're pretty limited on time, so I'm going to ask that for our 8 speakers here that we save our questions until the very end, at which point, once they have all had a chance to present, you will be able to ask questions in open Q&A. I'll also be keeping the introductions relatively brief in order to accommodate that. So, that being said, I would like to start with our first presenter, Han Kai, who will be presenting on uncertainty representation for space object tracking using outer probability measures.
Thank you, Michael. Good morning, everyone. In this presentation, I will introduce our recent study on uncertainty representation using the outer probability measure theory for space object tracking. There are 4 sections, and let's start from the background. Here are some objectives. The first is to explore the use of the OPM theory for model the information, actually some incomplete information for all of the uncertain components in a space object tracking framework, and then develop a possibility Bayesian filtering algorithm to integrate all these OPMs. And the third is to achieve advanced tracking performance by introducing the TLE data with uncertainty described by OPMs. Okay, in an uncertain system, the uncertainty can be decomposed into the aleatory part and the epistemic part. The aleatory uncertainty can be seen as random and characterized by a probability distribution. But the epistemic uncertainty is non-random. It results from the lack of information and cannot be modeled by a probability distribution. Alternatively, we can use the OPM theory to achieve a more relaxed uncertainty representation. An OPM can be seen as the upper bound for probability distribution. And the simplest form of OPM can be written as this equation, where the f is the possibility function. The most commonly used is the Gaussian possibility function, and it can be easily transformed to a Gaussian PDF. The difference between these 2 types of function can be illustrated in this plot. It seems a kind of low resolution, but we can still observe the right one is the Gaussian PDF, and at the increase of the variance values, the Gaussian PDF is less likely to assume any states, while the Gaussian possibility function assumes any states becomes more uncertain. Based on the OPM theory, we can derive a possibility Bayesian filter. The major advantage is that it does not require we have perfect knowledge of all uncertain components in the system. So, in space situational awareness, there are several uncertain components that we don't have some statistical information of their accuracy. In this scenario, we can use the OPM theory to bound their uncertainty and use the possibility Bayesian filter to achieve more robust tracking performance. This flowchart is the possibility filter developed in this study for space object tracking. And there are 3 major uncertain sources. The first is initialization, the second is prediction, and the third is update. In the next few slides, I will briefly introduce how can we use OPM to achieve a more relaxed uncertainty representation, and how can we design a possibility filter to process these OPMs. Okay, the first is initialization. Normally, initialization can be seen as the IOD process, initial orbit determination. And the admissible region method is a popular and efficient IOD method. In this study, we developed a possibilistic admissible region approach called PAR+. The PAR+ is able to handle both the aleatory and the epistemic uncertainty that introduced to the admissible region. The result of the PAR+ is a set of particles to populate the admissible region. For example, in this plot, the particles represent the PAR+. But we don't have further information to specify which particle is more likely than others. So the possibility of each particle to be the true state equals 1, meaning that their weight equals 1. So the PAR+ results in an OPM representation of initial orbit state. Dr. Islam Hossain will give a more general description of the power-plus method this afternoon. In the prediction step, we can propagate the OPM forward using this formulation, where the uncertainty will be introduced by the orbital propagation process, and it can be modeled by a Gaussian possibility function. In the measurement update step, we can obtain the posterior by correcting the prior using this formulation. If the measurement is the TOE data, we can bound its error, use a Gaussian possibility function by evaluating the specific angular momentum and specific energy. We use these two quantities because they are very stable and can be more easily parameterized. And the error bound can be obtained by a training process, assuming we have some reference data. For radar measurements, we can still use a Gaussian possibility function to bound its error, but the error bound we obtained based on some prior knowledge. Note that even we have some prior knowledge, characterizing the observation error is still very complicated because the observation mechanism behind it is very complex. Another thing you need to know is that the radar measurements are pretty accurate, so they may easily result in particle degeneracy. So we further developed a Gaussian max mixture update step. This method is not proven to the particle depletion and more robust to sparse measurement scenarios. Okay. To validate the proposed method, we designed a scenario space object tracking using real radar measurements and the TOE data. The targets are selected from cube-sized constellations operated by planning labs. We have some real radar measurement from LEO labs, and the ground truth is constructed using GPS data from planning labs. The big table shows the parameters of the 5 tested targets. Each target will be tracked for around 2 to 3 days with a couple of TOE and radar points, and some filter-related parameters are shown in this table. Oops. I don't know what happened to this figure, but I'll try to explain it clearly. In the first case study, we evaluated the map state error of a single target, OE20, and the top figure is the map state error position, while the bottom is the velocity. And the red and the blue vertical bars represent the time of radar or TOE update, respectively. Well, the red curve is a result from radar-only scenario. The blue curve is a result from using both TOE and radar-ized measurement. So we can say the use of TOE can significantly improve the orbital state estimation, and the result can be further illustrated in the IC frame. In this slide, we projected the map state to the angular rate space. We can say the TOE is able to eliminate a large portion of insignificant particles and thus improves the orbital state estimation. In the second case study, considering we have a couple of objects in your same constellation, they have pretty similar orbital shape and orientation, so their specific angular momentum and energy are also pretty similar. So the question is, can we use a common possibility function to bound the error of TOEs for all of these targets in a constellation? So in the second case study, we applied the Gaussian possibility function of a target to multiple targets, and the result depicted here. We can see the tendencies are pretty similar to previous one. And here are some conclusions drawn in this slide. Thank you.
Our next speaker will be Daniel, discussing the assessment of in-house developed reentry prediction methods.
Good morning. The author of this paper is Dr. Pooja Dutt. She's working in Applied Mathematics Department in Vikram Sarabhai Space Center. So this presentation went a couple of times for the review, and it was like blackened out, and it went into many iterations, and I got the final version only 2 days back. So I'm just going to read most of the portions because I am not able to fully grasp what she has done. So I'll just start with maybe we'll explore the whole thing together. This is the thing is it has gone through a lot of iterations, and the final version is done in a bit of a hurry because we had to submit it within 1 day. So it's basic whatever you will find in any nominal textbook. So I'll just skip this. The input data is the normal TLE, which is available publicly on the internet, and propagation is done with the SGP4 propagator, and conversion of mean elements from TLE to oscillating elements introduces error which are propagated further, and the inaccuracies associated with the prediction of the density of lower layers of the thermosphere, which is responsible for drag resulting in decay. So these are the uncertainties related to reentry prediction. This program is basically built on STK, and it's a MATLAB program built on STK using modules from the STK. So the response surface methodology with the genetic algorithm is used, and the optimizer is the STK optimizer, and the prediction of lifetime is done with the STK. So it's just one or two MATLAB modules over the existing STK software. So the inputs are whatever I just described: the space weather file, the set of TLEs, and the propagator. Actually, yesterday I had to email her and find out what is BC. So BC is ballistic coefficient, CDA by M, and the inputs are space weather. This is actually the previous slide put into a flow chart. This is embarrassing. The thing is, I got the presentation just yesterday, so it was tough going finding out what was happening. This is again the same thing put into a different slide. So the software was tested for existing some reentry objects, and electron rocket body is a second stage, and it was launched from Rocket Lab, and it was the tests were done, and the predicted the predicted versus the with the new model it was tested, and these are the dark one is the actual predicted reentry time, and the upper bound and the lower bounds are shown here, and In conclusion, the accurate estimate of reentry times and location of the uncontrolled reentry objects is very important. The major parameter influencing the reentry time predictions are discussed. 3 methodologies for estimation of reentry time of the space objects are presented here, and response surface method with GA, and optimization using the STK propagator, lifetime optimization using STK propagator, and a couple of case studies are done with the module, and all the 3 methods described here are comparable, and these are the conclusions. I should apologize for the presentation. Sorry. Thank you.
Our next speaker will be Yue Deng, discussing the impact of ionosphere, thermosphere, mesoscale structures on space environment specification and forecast.
Hi, my title is slightly different from the title in the abstract. And actually, I'm going to talk about electrodynamic forcing on the space environment specification. Sorry about that. And this is done through the collaboration between the UT Arlington and the UT Dallas. How can I flip the page? I'm sorry, just this one. I see, thank you. As we know, the space environment includes the sun, solar wind, magnetosphere, and the ionosphere, thermosphere. Due to the interaction between the magnetosphere and the ionosphere, the electrodynamic force actually brings a lot of energy and momentum into the upper atmosphere. Here just shows the field and current from the magnetosphere close through the ionosphere current, which set up a large-scale electric field and also bring lots of high-energy particle precipitation into the upper atmosphere. Here shows the observation about the field line current from the swarm data and the large-scale electric field from the DMSP satellite, and also the aurora particle caused by the particle precipitation from the timed GUVI observation. And it's there. However, this energy input varies quite a lot in the space weather storm conditions, especially. In the storm condition, the energy can increase dramatically, cause atmosphere expansion. And the atmosphere expansion can increase the satellite drag along the satellite trajectory. And when that happens, the actual position of the satellite could be different from the predicted position, and we call it a satellite tracking problem. After a superstorm, the blue line shows the index indicates the superstorm happens, the satellite tracking problem can be severe. Therefore, the knowledge of the accurate satellite orbit and the speed has been an operational concern. And this has particularly brought in light after two commercial satellites collided each other, unfortunately, in 2009. And they left thousands of debris in the space environment. And actually, the atmosphere drag is one of the biggest contributors to the error of the satellite orbit. And we definitely need more accurate specification or description of the atmosphere distribution along the satellite trajectory. Here I'm going to show you an example of the density during a moderate space weather storm. Here shows the solar wind conditions. And anyway, whenever the red line goes below 0, indicates storm happens. So the model we are using is a global first principles model, GITTN, Global Ionosphere Thermosphere Model. And we can fly the satellite in our simulation to extract the neutral density along the satellite trajectory. Then we can compare the simulation from our theoretical model with the satellite observation, GOCH satellite. In the quiet time, we're doing reasonable good job, but in the storm time, the enhancement from the theoretical model is lower than the observation. Several mechanisms can contribute to this underestimation, and one possible mechanism is the spectrum of the energetical particle precipitation. Typically, the Maxwellian distribution is assumed for the energetical particle precipitation in the aurora region. However, the satellite observation indicates there is a substantial underestimation of the soft particle precipitation. The question is, how important is that soft particle precipitation in the aurora region? We did a little bit of comparison between the observation, black line, the GOCH satellite observation, and blue line or yellow line, that's the default run from our theoretical model. And the red line is the improved model from our GITTN simulation, and by including the soft particle. including the soft particle definitely improve the comparison with the observation. And the question is, how can this influence the satellite drag? And here we show the integrated mass density along the satellite trajectory, because satellite drag is more sensitive to the integrated mass density along the satellite trajectory. And we start the integration from the beginning of the storm. The black line basically shows the density from the empirical model, JB. JB is an empirical neutral density model, which is currently used in Air Force for the satellite drag estimation. And the red line is the observation from the Gauge satellite observation. And clearly, there's some discrepancy between the empirical model and the observation. And the blue line shows the improved theoretical model. By including the soft particle precipitation, the simulation changed from the green line to the blue line. So improve the agreement with observation. This quantitative comparison, of course, changes from case to case. So more statistic study is needed before we draw a solid conclusion. But at least in terms of the mechanism, the soft particle is an important mechanism for the neutral density enhancement along the satellite trajectory. The main conclusion is the electrodynamic forcing is very important for the specification of space environment, and including the soft particles helps the data model comparison. And the integrated mass density, which related with satellite drag, is subject to the influence of electrodynamic forcing. Thank you.
Our next presenter will be Daniel Zhang, discussing the Orbital Catalog Toolkit, a software suite for catalog maintenance.
All right. Hello, everyone. My name is Daniel Zhang. I'm here from MIT. I just started as a student in the PhD program last year, along with Miles, or who's part of my team. We are looking at creating this catalog toolkit. Just to give you a quick background of me, I've worked at MIT Lincoln Lab for the past about 7 years in the SSA side of things, working on a lot of the telescopes, a lot of the radars that span from Kwajalein to Socorro, New Mexico to Massachusetts itself. And we had a lot of tools at our disposal to use to do a lot of our analysis. But then when I came back to academia, I found that it's not as readily available as perhaps some of the in-house tools that we saw. So we began our trek into creating our toolkit. And many of you might have your own, and you might be thinking, why are we creating another one? There's already too many, but as you'll see, we have a lot of bits and pieces here and there, but I'd like to connect all those dots to make it easier to do research in this topic. So I don't think we need to belabor the point that SSA is something that's very important, and there's a lot more research interest in this area, especially as government, as the world leaders are coming to the conclusion that it is very important and a very finite resource. So what do we do with this? So to give you a quick look at the SSA processing chain, I have just this graphic for you. You can see, first, we have to be able to see the satellites. So we need to take a look at that, usually using optical telescopes. SST for me means Space Surveillance Telescope, until I learned yesterday that it doesn't necessarily mean that. And also Millstone Hill, which happened to be, like the radar in case here, the first SSA sensor to see Sputnik. And that we use these types of sensors to look at objects up there. And you can see the Starlink, the train pass by over Missouri there in the image. And we see data like this. So what do you do with that data? So you first have to reduce that data, which is to say you have images for optical or radar. You have your range and ASL measurements and perhaps Doppler. With that, you want to reduce it into where are you actually pointing? Where is that dot in relation to the celestial sphere? So you create text files in essence. So you have some states with some hopefully good timing data. So after you reduce the data, you want to do association and correlation. Association, which means which dot goes with which dot, because frame to frame, you might lose track of which goes with which. So you don't know what it is yet, but you do know that that goes with another object from previously seen frames. Correlation, which we talked about a little bit earlier and yesterday, which is just figuring out which dot that object is. So is this an object that we know in the catalog? We know that it was launched on this date, perhaps. We know we've seen it before. Or if you don't see it, as you've also heard earlier today, you then create an uncorrelated target, or UCT, which is a big problem for a lot of the SSA type of work. After that, you either create a UCT track and do an IOD, initial orbit determination, to create orbits, or you update the orbits that you already have after correlation. So which is say you can use batch filters, or you can use a sequential filters such as extended Kalman filters to update your orbit. After that, you can do the things that we really want to do, which is to analyze. So if there was a maneuver, can you figure out when it was, how big that burn was? Or if you want to do some sensor tasking work, if you want to reduce that uncertainty of an object, reduce that covariance, which sensor do you then task? Is it going to see it at this time? If it's too big of a covariance, what kind of search strategy do you want to employ? And conjunction analysis that we talked about earlier as well. All those things you want to do, but you can see there are multiple layers to the SSA problem, and there's this big flowchart that we want to be able to do. So what exists today? We talked a little bit about the existing catalogs, catalogs from government, such as our own US Spacecom's SATCAT. So this has gone back decades, and this is really the premier go-to catalog. I asterisked it twice to say it's kind of open because, as we talked about earlier, it doesn't show every object that's up there. It probably won't. So it is a very good catalog, but it is limited in some senses. Then, of course, there's commercial. We have a lot of you in the audience here. Thank you for all of your work pushing this area. Availability, I just wrote as closed because that is the business model that you're trying to sell that information. TrueSat is another example that's a little bit different. It's the open and crowdsourced method to just really let's have the masses get out there, use their phones, use their own astronomy telescopes to figure out where things are. So that's another avenue for which you could use as an existing catalog. Now, of course, those are the existing catalogs. So what about tools? What if you want to create your own catalog for your own lab? Or you want to do, are there interesting experiments? You want to do validation? You have these types of tools that are existing. So Dr. Kelso also showed with Celestrak that there's a lot of astrodynamic software that we probably are familiar with for orbit determination, orbit update process from the previous chart. Astronomy.net might be used for partially doing data reduction, so figuring out where you're pointing in relation to the stars. You could have Astriograph, which also has a library called Orbit Determination for Python, Orbit Update, which does sequential OD and propagation, and of course ORCID, which was mentioned earlier as well, for a lot of the astrodynamic types of low-level libraries. So there are tool sets here and there, but as you can see from the previous chart, it might not connect all of them together. And of course, this is not an exhaustive list. There's a lot from the astrophotography folks out there. There's a lot of astronomy softwares out there too, but it is a little fractured in my mind for any budding researcher to come in easily and just take a look and really implement their ideas. So for our catalog toolkit, some of the goals that we want to accomplish is really fulfill this full processing chain of catalog maintenance. So that's all the way from perhaps taking images. Let's say you have an image, data generation, how do you do that, data reduction, all the way down to analysis and really be able to support some of the cool research that's going on. And as you've heard here from the panelists, how can we support that in an open source and accessible way? We really want to aid in the development of these kind of algorithms, and some of those are listed here. One example is shown on the bottom right for some LEO passes. How do you do sensor tasking for these types of multiple things overhead? This is particularly a problem if you have a small field of view sensors. So if you're trying to do SLR, satellite ranging, or if you want to do satellite imaging, how do you do that easily? So some of the functions are shown here. It is currently MATLAB-based, and hopefully it'll be extended to Python, where there are a lot more libraries available, but not to toot Massachusetts a bit, since MATLAB is based in Massachusetts, but it is very available for a lot of the research institutions. So we are developing there first. It is using the ORCID library for a lot of the low-level stuff, and you can see some of the things that we're trying to do here and some visualization suite. Use case one could be UCT processing. So if you try to correlate, if you have a set of images and you determine that that is not in the catalog, after you do compare it to some catalog, what do? Then you do hopefully an IOD with the data that you have. If it's angles only, if it's a radar, we're able to process those and then create that line and add it to whatever catalog we're ingesting here. And perhaps from that point, we can propagate it and then take a look at what sensors might be able to see it and then be able to task that. Another case might be if you have multiple sensors, how do you do this in terms of optimizing for covariance and uncertainty across the entire architecture? So architectural level studies hopefully will be what this is also used for. So there's a lot of things that we want to do. Please come talk to me. There's a lot of, hopefully there will be more collaboration and any comments and any of the best practices that you've learned yourself. Hopefully we can learn together and make this open and really inviting for other researchers that are upcoming. And that is it. So if you have any questions, if you've gone through some of this pain yourself in developing your own software, please come talk to me. I'd love to pick your brain and see what we can learn from each other and what we can make open. Thank you.
Our next presentation will be from Daniel Kucharski discussing Quanta Photogrammetry for biometrically inspired space object recognition.
Thank you. Going to the next slide. So what we are doing here at the UT, we are developing methods for satellite identification and recognition. The space object recognition and unique identification is possible with photometric observations, and we are developing an RSO fingerprinting method that generates a unique identifier for an object based on the reflection pattern produced by this object, and we are talking about solar reflections only. We aim to measure unique photometric fingerprints of the satellites that will be used in the three-step identification process that includes enrollment, verification, and identification, and these stages are presented in details on the right side. So basically, we want to measure photometric fingerprint of the satellite, characterize features in this fingerprint, process that, and generate some digital ID for given object. To do this, we need to move from typical imaging technology into faster and more accurate photon counting systems. And here we are collaborating with Grad's satellite laser ranging station that has developed and implemented photon counting system at the observatory for satellite observations. Active satellites, defunct satellites, and space debris objects located at different orbits from LEO to GEO. So what this photon counter does is the telescope collects solar photons reflected from the sunlit object, and then the photons in the wavelength range from 780 to 900 nanometers are directed to the photon counting system, and the photons are detected by highly efficient spot detectors, time-stamped and recorded in the output files. And here on the left-hand side, you can see just an example of single photon light curve of Topex Poseidon. This is spinning satellite, and you can see repeated pattern which represents change of satellite brightness as it spins during a single pass. So this system it works. We receive test data from that system, but we also work on, we have developed our own photon counter, a low-cost device here at our research group CAST, Computational Astrodynamics Group. And the sensor, this is hand-sized device. It's sensitive and very compact. It operates on low power current. It uses a Hamamatsu photon counting head with 50 megahertz sampling rate at high sensitivity over the visible range. This is the red curve on the left bottom plot. It shows sensitivity of that sensor. We also use, in this development, we use a PC board. This is BeagleBone Black that includes CPU and 2 real-time processors for real-time operations, and also a GPS mouse for linking this device with UTC timescale. That's for timestamping. And also we have real-time operation software for data collection and transmission. So based on single photon detection systems, we are developing Quanta photogrammetry method. Quanta stands for single photon, and photogrammetry is a method of generating photograms of satellites from the photometric data. The method utilizes hypertemporal light curves at the single photon resolution to generate photograms that can be used as a unique fingerprint in the satellite identification process. So in this example, on the right-hand side, you can see phase-folded light curve of Topex. It's a single pass, 11 minutes pass, and due to change of observation angles, we can see that the satellite gives us different the photometric pattern, photometric reflections produced by the satellite is changing throughout the pass and represents a mixture of specular and diffuse reflections, with the specular reflections being the spikes, high intensity short flashes, and all the rest is more or less kind of diffuse reflection. By taking what we need to do to generate photogram out of such light curve is to transform or process measurements through transformation matrix, which is basically satellite attitude transformation matrix, project photometric observations onto satellite body fixed frame, so that particular samples, photometric samples, refer to the specific location in the satellite fixed coordinate system. By doing that, we are removing time dependency from the photometric pattern, and we are getting photogram that is fixed with the satellite structure. Here are 2 examples of Topex, 2 different days, and what you can see is the same pattern with similar or the same complex geometries. Just in the center, we have high intensity reflection from the front of the solar panel. Then we have different features produced by different sides of the satellite. This is Mulvady projection of the photometric data and polar plot. We also can see effects of self-shadowing on this type of projection, which decreases photometric intensity. And my conclusions: the single photon hypertemporal light curves allow generating high resolution photograms with the complex geometric patterns representing the RSO's external structure. The photometric fingerprints, such as those photograms, can be used as the unique identifiers in the process of RSO categorization and recognition. The biometric algorithms applied to the RSO fingerprints can automate the space object recognition methods. And also we want to point out that geographically distributed network of photon counting systems is needed in order to improve the data yield and populate RSO fingerprint database. So that's it from me. Thank you. Thanks. Thank you.
Our next presentation is from Nathan Ryland discussing minimum space occupancy orbits for satellite mega constellation design.
Thank you. So the motivation for this research is something that I'm sure all of us are familiar with. The deployment of the OneWeb and SpaceX Starling constellations will have a huge impact on the amount of objects in low Earth orbit. And based on our sources, we predict that this will increase the number of objects in LEO by about 46%. So the goal of this study is to demonstrate that minimum space occupancy, or Meso orbits, which are a generalization of frozen orbits, can greatly reduce the risk of endogenous or intra-constellation close approaches within these proposed megaconstellations. So a little bit of background on what exactly a frozen orbit is. So these frozen orbits correspond to equilibria for the average equations of motion under a particular dynamical model, which is the purely zonal model. And this work was first published by Cook in 1966. So in okay, well, the laser pointer is not working, but the figure on the right shows the components of the eccentricity vector, which is composed of the eccentricity and the right ascension of the argument of perigee. And we consider an orbit to be frozen when this eccentricity vector stops moving, or in other words, this could be when the rate of change of the eccentricity and the argument of perigee goes to 0. And these conditions are met in the equations up there. And where the zonal terms come in is through this k and these c terms. And the orbit freezes when you balance the contributions from the even and the odd zonal harmonics. So as such, it would seem obvious to simply place your orbits in the closest, in orbits that are as close as possible to frozen orbits in oscillating space, so that as your orbits precess, they sweep out the least amount of volume with respect to time. Because if its orientation is fixed in space, you can imagine that it will be taking up less volume as it precesses. Unfortunately, the solution is not this simple, because frozen orbits don't actually exist in the real equations of motion. And once you introduce the short periodic terms and your equations, your eccentricity vector begins to move around. So despite this, frozen orbits, when recast in oscillating space, are still much better in terms of minimizing volume than their non-frozen counterparts. And you can see this on these plots here. So this is once again that eccentricity vector. And you can think of how much area is colored as a proxy for how much volume this particular orbit will sweep out as it precesses. So on the left, we have a frozen orbit. The dot represents that frozen orbit in mean space. And the orange concentric circles represent that in oscillating space. And then on the right, we have the same thing except for a non-frozen orbit. So you can see clearly that the frozen orbit still sweeps out much less volume than the non-frozen orbit. So unfortunately, this is still not sufficient to minimize the volume that orbits will take up. So in order to account for these short periodic terms and additional perturbations which destroy the frozen orbit condition, we use a high accuracy orbit propagator thalassa with a sufficiently complex force model to search for the perturbed Keplerian orbits, which sweep out the least amount of volume in three-dimensional space. And similar approaches have been taken in spacecraft formation flying, where they attempt to reduce the relative drift between a chief and a deputy satellite. So to further highlight my point that just freezing the orbits or even just stacking different planes is not sufficient to keep satellites at a constant relative distance, I plotted the major axis of a couple of different variations of the OneWeb constellation over just one day. So Meso is the minimum space occupancy that I mentioned before. This nominal is what's given in the FCC reports. The control is simply staggering the different orbital planes, and then the frozen is finding the nearest frozen orbit and then also staggering the orbital planes. So you can see that even in the staggered and the frozen, there's still a lot of crossings of the semi-major axis, while in the Meso configuration, the relative distance between the different orbital planes remains fixed. So in order to test whether or not this theory can be effective at reducing the number of close approaches experienced by megaconstellations, we performed 2 case studies. The first was on the OneWeb LEO constellation, which you can see here. It's around, I think, 1,900 satellites. And the process for determining a Meso configuration is we find a Meso. Well, for every single nominal satellite, we find a corresponding Meso satellite. And as you can see in the plots here, the initial states and the ground tracks are almost indistinguishable from the nominal counterparts. So then we use a brute force simulation approach to just do a lot of propagations and measure the close approaches that occur. So you can see in the top 2 plots a comparison between the nominal, which is the FCC report, and then our Meso configuration. So after 90 days of operation, the number of close approaches less than 1 kilometer that are experienced by the Meso configuration is significantly less than the nominal. And the same can be seen for the control case, which is just by simply staggering the planes. And what I think is even more remarkable is what you can see in the right 2 plots, where the approach distance of the Meso configurations is bounded around 5.5 kilometers, while the approach distances experienced by the nominal and the controller staggered configurations goes almost to 0. So the same type of case study was performed for the Starling Constellation, and here's just a little table that kind of briefly shows what that configuration would look like. Here's a plot of that. And the Starling Constellation is a little bit different from the OneWeb because it's separated into 5 different types of distinct orbital shells with unique semi-major axis and inclination combinations. So we follow the same procedure as before, and we find a Meso counterpart for all the nominal constellations. You can see all the satellites in the left, and then in the right you can see the distinct orbital planes. And once again, the Meso counterparts are almost indistinguishable from the nominal in their initial conditions and their ground tracks. And we see similar types of increases in performance in the OneWeb Meso configuration versus the nominal. Now, like I said, there are 5 different shells. These are just the results for 2. But similar to with the OneWeb results, you can see that the close approach distance is bounded around 0.5 kilometers, and the frequency of approaches is much less. So a summary of the key findings, what we found is that Meso is very effective at reducing the number of close approaches that are experienced by these 2 megaconstellations. In these 2 tables, you can see some more detailed numbers on that. What I think is nice is that the nominal for the OneWeb has a minimum close approach distance of 0.006 kilometers, while for Meso, like I said, it's about half a kilometer. The performance was a little bit worse for Meso for Starling, but it was still a lot better than the nominal. So in conclusion, megaconstellations can't be designed just based off of Keplerian motion, and the mission design from inception to end of life must take into account orbital interactions and the evolution of the environment. And we found that the adoption of Meso orbits can significantly reduce the risk of intra-constellation close approaches. And if you want more details, you can find them in this preprint of a journal paper that we've recently submitted. Thank you.
Our next speaker will be Jason Stosh, discussing multi-source resident space object state validation and fusion.
All right, thanks, Michael. And thanks to the organizers of this great conference. It's a great opportunity to share the work that we've all been doing and learn a lot from each other. I'm going to be presenting some validation and fusion results that we got from multi-source resident space objects. So, All right, so motivation. If you're not properly motivated, you haven't been listening. Diane did a great job of motivating us this morning. Go big or go home. You didn't go home, so we're going big. So this is a plug for Morba's astrograph tool here, just a screenshot. And we've been motivated by the acceleration of the number of RSOs that's happening right now. There's tremendous growth in the number of RSOs. But what we also see with this pull-down menu here, as an example, there's also an acceleration of the number of data providers that are out there, right? We've got commercial providers, we've got academic providers. We saw yesterday we have a plethora of international providers. There's a lot of data that's coming into the scene. So the motivation is, how do we use that plethora of data to increase confidence and aid in decision making? So that kind of motivated our work here. I'm going to talk about two things. One is multi-source validation, an assessment of the accuracy of multi-source data. The second is fusion. How are we going to take this data, fuse it together to come up with a better solution? All right, so for this, this state comparison or this error assessment phase, we participated in this SAC-T event that Jason brought up and Diane brought up. It's a great exercise. It's a real-world exercise using real commercial capabilities combined with government capabilities to really showcase what the commercial community is capable of. It's an impressive exercise. It was a week long back in December. So what we did was we took data from the UDL, and you can see the Unified Data Library. All those boxes represent a different provider that's providing data into this repository. So we ingested data from 3 different providers, Numerica, Leo Labs, and the 18 Space public catalog. And we also ingested data from MITRE and Spire as our calibration source. And the data that we ingested was state information. So basically catalog information from these different providers. And we compared the provider states to the calibration states.
Quickly, just kind of talk 10 words or less what the data curation bubble is.
No, I can't. We can talk afterward. I got to keep on my agenda, but some of that might become clear. So these are the results for GEO and MEO. Across the bottom, we've got about the week-long period of SAC-T. The errors, the error axis, from 0 to somewhere on the order of 15 kilometers. Blue triangles are 18 space, the public catalog, so the errors associated with those TLEs. The orange circles are Numerica data, the commercial provider. So that just kind of gives you a nice visual comparison of the errors of these different sources. And then the next page shows the numbers behind that, the position error, RMS, and then broken down into radial, in-track, and cross-track. And then some of the numbers on the amount of data that we were able to process. So these are the Leo results. Again, blue triangles are 18 space. Orange is a commercial provider. In this case, for Leo, we're showing Leo Labs data. And I'm just going to let that speak for itself. On the next chart, these are the numbers behind it. Again, the numbers speak for themselves. That radial RMS is impressive. Sub-meter level accuracy. So some might look at those plots and they might say, okay, who's right? We can use these plots and who's right. But what we like to focus on, what we assert, is that all of us can derive more confidence than any single one of us, right? I think we all know that, and that's what we're working for. So how are we going to do that? So what we did in this little study was state fusion. How are we going to fuse states from different providers to get a more confident solution? So again, we're ingesting data from the UDL. We focused on GEO for this study. So we have the 2 providers that we're trying to fuse are Numerica and 18 space TLEs. And then the calibration states come from MITRE. And the calibration states I should mention are precise navigation solutions. So in the case of MITRE, they provided GNSS satellite states. In the case of Spire for LEO, they have their own onboard precise orbit determination solutions. So these are high accuracy calibration sources. So we chose to investigate a supervised machine learning model. So to form our training set of data, we took a state from one of the providers, propagated it forward a randomly sampled time between 0 and 48 hours. We took the state from a state from the other provider for the same RSO, propagated it forward to that same time, and the Cartesian states of those two objects, along with the propagation time of each object, represented the model inputs, and the model response is the truth, the calibration position and velocity. We also generated a test set of data using that same procedure on an independent set of RSOs. So same regime, but different RSOs, because we wanted to say you can train on some RSOs and apply that model to different RSOs in the same regime, of course. We tried 19 different regression models to see what the different regression models results were. And these are the results for the best regression model we found. This is a busy chart, so let me explain it. Along the bottom, this is not time. Typically, you see time along the bottom. This is actually just test point. So for each one of those points, it's taking one provider, propagating it forward a random amount of time, another provider, propagating it forward that same amount of time, and then the fused solution. So the triangles are 18 space alone, the errors associated with 18 space. The circles are the errors associated with numerica, and the green circles are the fused solution. So the numbers on the right, you see they're different, right? They're larger than what we showed for the state error estimates, and that's because they include propagation. And our propagation models, we did not attempt to match the propagation models of the providers. And to some extent that's intentional because oftentimes you won't be able to do that, right? And so one of the things that we found in this study is we were able to account for some of those propagation errors with this method. So getting to the conclusions here, again, just restating. Up front, the commercial providers rival, if not exceed, the performance of the existing public catalog. One of the major key findings is that next sub-bullet is we identified while we're going through this the need to not just aggregate, but also curate the data from the different providers into a common language. Not all providers provide their data in the same frames, even the same data types, that sort of thing. So the curation, in order to be able to compare and later fuse this data, curation is key. And then our second findings is that the multi-source data fusion via supervised learning could improve on the individual solutions. And it applies across RSOs in the same regime. And of course, more accurate orbits lead to better analysis for sensor tasking conjunction analysis. So bottom line, as we get more and more RSOs, more and more data sources, multi-source analysis will significantly improve confidence in complex decision making. Of course, we want to thank the data providers who collaborated with us, answered our questions, provided the data that we could do on this. It was a great data source, and we very much appreciate it. Thank you.
Our last presentation before Q&A will be from Di Wu, discussing detecting resident space object maneuvers using proper elements. Thank you.
Well, thank you, everyone. So I'm Di Wu from University of Arizona, and I'm very honored to share with all of you our research work in space object maneuver detection using proper element to finish our great session where we cover a lot of things in SSA and STM. So it's a collaborated research between our university and some Australian engineers and scientists. Oops. So sustainability is the thing that brings all of us come to Austin, and for all the SSA and STM, with all the development beside data, there's a high requirement of bringing enlightening ideas and solutions from academia to solve all those problems. And what's more is openness and transparency, just as T.S. Kelso stated at the start of this conference. So in terms of maneuver and event detection, the trustworthy information extraction method is the most important one. And Tom Callacy once written in his paper saying no single bad set of algorithm parameters exists for all satellites under all conditions. And we say, that's probably true, but maybe you haven't considered about proper element. And we're just trying to provide some other insight and aspect into this field, and maybe also for some other things we're actually looking into. All right. Too much. Okay. One more slide. So I'm just going to give a short introduction, go back one, about proper element. Yeah, this one. Okay. So I just gonna give a short introduction about proper element, and it comes from the mean. We can see that the mean oscillating of our eccentricity is like this, and this vector evolution could be composed of like two vectors. The first vector is called proper eccentricity vector, which is fixed in length but rotating in the space, and the second vector could be is called the forced eccentricity vector, which is both fixed in length and fixed in direction. And same thing happened for the evolution of mean inclination vector. It's also composed of these two vectors, proper inclination vector and forced inclination vector. So what is so significant about this proper element? So it all just seems to be some mathematical concept that, like, you can do the plus, you can do the minus, and you make confusing names for them. So to understand this problem, we need to go back into the root where this proper element is actually developed and invented, back to the asteroid family association problem, where you can see all those little asteroid actually belongs to the Asian big asteroid. Say like Dora there, it's actually composed of like tons of like different asteroids there, but they all share the same proper element. But say nowadays, like if Dora took a maneuver, but we know it's an asteroid, it cannot take a maneuver. But if it takes a maneuver in the space, what does that mean? That means like it's no longer Dora. It's probably Gora or Godzilla, some alien object over there. So this proper element, instead of providing the information of circumstances, it actually provides the information, the natural element information. And the maneuver will change this natural elements. So we see this is a pretty good concept. Can we reproduce this theory in the near Earth space where we have all the real problems? And yes, we can. So this is a propagation setup where we have this 20-year orbit propagation osculating domain where we include 15 by 15 zonal tensor harmonics from Earth's gravitational potential. We take sun and moon perturbation. We take atmosphere drag. We take solar radiation pressure. We basically take everything. And you can see that clearly we reproduce our theory, and clearly there are the existence of proper element in this case. It's a little bit lagging. All right. So if we take a look at the evolution of our oscillating mean and proper element, what does it look like? So you can see that the blue line is actually our oscillating element, and it's just like oscillating all the way. And the red one is our mean element, which is meaning our oscillating element. The most amazing thing happening in the proper element space, you have to focus on the scale of those two things. So it's actually the mean, the proper element is actually stays quite constant around one value, especially if you do the comparison with osculating and mean element. So if we take a small delta V maneuver in our satellite, this is what it looks like in the proper element space. So what happened is, before the maneuver, your proper element stays around one value and just jump around. And at the maneuver, the proper element changes. And after the maneuver, it stays around that value. So it looks like jumps around ups and down. What is the distribution looks like? So this is what distribution looks like. The blue one is the pre-maneuver distribution, and the green one is just like post-maneuver distribution. So for the pre-maneuver distribution, you basically just like stay here and jump around, and at the maneuver, you jump from our blue region into our green region, and you stay here and jump around. So beside this one, we can also see that we can use a Gaussian distribution to pretty good approximate the distribution of our proper element, no matter it's like post or previous. So since I have 1 minute, so this is just without a setup, like proper element and distribution, and especially the relationship between maneuver and proper element. This is a showcase where we can have something like a Bayesian online maneuver detection using the proper element. And we can clearly see that it's simple, that we can detect it. Yeah. So the main takeaway from this one is proper element as a natural element. It provides some information that may be critical to some of the SSA problem. For now, we showcase the maneuver detection one, and maybe in some of the MIT stuff that we can collaborate, maybe in some other things. That's all. Thanks.
So at this point, we have about 5 minutes for any questions.
Hi, I've got 2 questions. Sorry for the earlier presenters. Your questions have just fled my mind. It was too long ago. But for the photon counting camera, what's the time resolution, and is it a single pixel device, or do you have any XY information in the focal plane?
So this is a single pixel device at the moment. We are thinking about going into single pixel camera, megapixel single photon counters, like Ruli or Quanta image sensor. And the timing resolution is some nanoseconds. It's less than 20 nanoseconds.
Okay, thank you. And for the gentleman from Slingshot, wouldn't it be easier to combine the observations instead of trying to combine the orbits? It seems like I know you're using TLEs, but as you mentioned, the TLEs aren't basically the best data, so you could use a couple of commercial providers, which you would mention seem to give you better results, and then you could actually go to the observations and fit orbits to the combined set of observations. So why didn't you take that path?
Sure. So that's a great point, and it's a valid point. Easier is a loaded term, right? Easier. Well, it's not easier in that you have to do orbit determination than to get state vectors. So that's possible, and we can do that. But we chose this is the first step that we chose, and this was something that we understood could bring some value to the community, was to just evaluate the state vectors. So of course that's upcoming work. That is future work where we'll take the observations. Although in some cases, for example, the TLEs from the public catalog, you can't have those observations, right? Those observations are not available. So we want to take all information from all different sources, and be able to combine that even when some of the information is not available. And apologize, I didn't mean to be rude about the not answering the curation, but we can certainly discuss the curation involved. In this case, it's maybe fairly simple things like frame transformations and so forth, but also it could mean things like how do you fuse a radar observation with a maneuver detection? And those things are very different data types. But there's data that's out there, so the curation is how do you map those? That's
I'll give you guys a quick compliment, though. Kind of piggyback on what Mark said. I think you add a layer of complexity if you're having to do orbit determination, because now you're talking about having to do calibration against the observations versus the actual orbit sitting the same vectors, teams, what have you. So I think to some extent, in order to go faster, we need to not let perfection be coming at the expense of good enough. So I really like the analysis on, hey, here's what's out there, here's what we can do with it, and it's not, requiring additional layers of processing or complexity. Because a lot of times it's just about getting enough good enough information to make a decision. So
sure. Take advantage of what you've got. Thank you.
I'll be quick. So my question's for the gentleman who gave the presentation on the satellite fingerprinting. I wanted to confirm that you don't need to know the orientation of the satellite to use this method.
We need to model attitude of the satellite to make that projection. But that's possible with light curves. You can, there are methods to calculate spin parameters of the satellites from light curve analysis.
And with that?
So that will be the end of the SSA Tech and decision-making session. I apologize that we didn't have enough time to get to everyone's question, but I'm sure if you reach out, the speakers would be happy to answer your questions. With that, I believe it is lunchtime.